Hi everyone, welcome to hours for Huffman Encoding. I know this is an awkward time, but we couldn't do it after the break just because if we did it, the first day after the break, it'd be due 2 days later. Huffman Encoding, and this is like me speaking out of my heart, is my favorite 106B assignment. A lot of the time when I went to lecture in 106B sophomore year, it was actually fall sophomore year, I was on my phone a lot of the time. I was like, sort of paying attention, sort of dozing off. But when we talked about Huffman Encoding, I loved this. I literally went home and started it the day I first read it, and I was like enthralled by it. I love Huffman Encoding. And I hope I transmit that over to you guys, at least maybe not love it, but at least appreciate it. This is an awesome assignment. And it definitely, like, the logic and the math and the graph sort of theory behind it is super cool. Who here has sort of, to start off, read the handout? All right, but sort of, right? So today we sort of assume that you have it, and we're going to go over what the algorithm is, what it's what it sort of does, why it does what it does, to sort of help you get an intuitive understanding of why it works. I definitely recommend you do that with this assignment, because similar to PQ, if you know what's going on before you sit down and code, it's going to be a much better experience for everyone involved. All right? Any questions before we start? Yeah. This can be a pair assignment. Yes. We have 2 assignments left. This and Trailblazer both can be pair. Good question. All right, awesome. So we're going to begin in a sort of a weird tangent, but I have to go the other way. Here we go. So when we look at a number, what is this number? 8,459. Now, when I would tell you, get this many beads, give me this many beads, how do you know how many beads that is? Why do these 4 numbers in that order, tell me, something about the real world? What is a representation here? It's decimal, right? But what does that mean? Yeah.
Each number is a digit times the power of 10.
Exactly. Each number is a digit times the power of 10. And so the first place is going to be 10 to the power of 0, right? The second place, 10 to the power of 1, and so on and so forth, right? This is the decimal system. Why 10? Because we have 10 possible things that can be a digit, right? And so that way, we can represent pretty much every single number, every single integer, right? In mathematics, which is kind of cool. So that's how that works, right? It's going to be 9 times 10 to the power of 0, plus 5 times 10 to the power of 1, and so on and so forth, right? Pretty simple, first grade mathematics. Binary. Binary works in the exact same way. Who here knows how to read this? Who knows intuitively what this number is? All right, we got here, sort of. Now, this works the same exact way. Now, in the same way that in the decimal system we had 10 things we can work off, and we're working with powers of 10, here we have 2 things we can work with, 0 and a 1. And thus we're working in base 2. So here, if you look at what this sort of looks like, it's going to be 0 times 2 to the power of 0, plus 1 times 2 to the power of 1, plus 1 times 2 to the power of 2, and so on and so forth. So it's actually identical to the decimal system, just that instead of having 10 things that we can work with, which allows us to work in sort of base 10, now we have 2 things we can work with, 0 and 1s, that allows us to work in base 2. So what is this number? What number does this represent? Yep. 6, right? If we look over, 1 times 4, 1 plus times 2 equals 6. Awesome. Any questions about binary? Sort of what it sort of looks like under the ground. It's a little bit tricky and kind of weird to think about, but after a while, you get used to the fact that, it's almost identical to decimal, just that I can only have 0s and 1s, right? And thus, in the same way that in decimal we can represent every number, we can also do it in binary. Now, a lot of the things, the computer, as we all know, works with 0s and 1s. And so when we try to represent things, we're actually representing things with 0s and 1s. And so this is the ASCII sort of table. And you guys have sort of somewhat worked with this under the covers. But the car type is actually a number that defines a specific character. So for example, A, lowercase a, is going to be, can we find it? Yeah, it's going to be 97, all right? Which is that number in binary, all right? That sort of makes sense. So every single character maps to a number of sort of bits. Now, to go over a little bit of terminology, a bit is just a single 0 or 1. A byte is going to be 8 of these. All right? Any questions so far? You may be a little bit confused about why this has to do with Huffman encoding. Now, let's say we have this problem. I have this number. Let's say someone comes to you. Let's say one of the Chris's comes to you and says, Anton, I am going home for Christmas, and I have a small piece of memory, and I want to write the word atata, which is actually the word for father in a language that now I cannot remember, but this is actually a valid Scrabble word, apparently. Now, he says, look, here we're using, how many are we using? We're using 48 characters for this. That's not, I don't have that much memory on me, but I want to still take this back home with me. What can I do? Now, something we can notice is that there's a lot of A's here, right? How can we work off of that? We don't have enough memory, right? How can we work off that? Now, a big issue is that A takes up a whole lot of space, right? Like here we can see A takes up 8 bits, an entire byte. Let's say I don't want that. Let's say, you know what? I want to actually make it do 2 things. I'm going to change the representation of what A means. And so I'm actually going to represent A with less characters. So if I go ahead and, let's say I initially arbitrarily represent it with just 0, 1. I just say 0, 1 is now A, right? Then this happens. Now instead of 48 characters, it's 24. So I created a new language where it's identical to the previous one, but now A has less sort of memory associated to it. All right? What's the value of this? Why do we want to sort of like do this? Why does this matter? Yeah. To use less memory, right? We have limited finite memory, and we want to be able to use our computers to the vast extent. We want to store all your pictures from your holiday vacation in Maui. And so stuff like this helps that. All right. Now, why did we pick A? Why did I not pick, T? Why did I pick to choose to represent A with less characters? Because it's the most frequent, right? A is the most frequent character. Now, how can we extend this idea? So I wanted to give less bits. I want to represent a character that was more frequent with less bits. How can we extend this idea? So we did it for A, and we did it for A just because our word was very short. But let's say that you have the compendium of Shakespeare's works, and you want to shorten that. What can you do? What can you do? So we're here. Yeah.
Give each letter a different, shorter value.
Gave each letter a different, shorter value. Now, the issue is that we can't just arbitrarily do this, right? Because if we have, the reason why the ASCII table is the way it is, so if we go back a little bit, we'll see that we have here we have 127 characters, but in reality there's 255. And it's because a byte can only store 255 things. And so I can't really store 255 things with less stuff, right? That's just impossible. But what I can do is represent frequent stuff with less characters and unfrequent things with more characters. All right? So it's sort of a cost-benefit analysis. I can say, you know what? I'm going to go ahead and represent A with just like 0, 1. Or in this case, 0, 0, 0, 1. Right? That's what A represents. And I'm fine representing Z with, all those different characters. Why is that the case? Why are we okay with that? Yeah, right? Because Z is not going to come up as often, right? And so what I benefit from having Z at long, from the cost of that, versus the benefit of having a short representation of A is huge, right? And potentially groundbreaking, right? Any questions about this? Sort of what we're trying to do. Now, this is sort of the basis for Huffman encoding, is that even though we have an ASCII sort of representation for these words, we can go ahead and we represent them in different ways, such that with less bits, we can represent the same amount of information. I don't know about you guys, but that sounds awesome. Like, that sounds so interesting to me. The fact that the same amount of information with less stuff, we can represent the same thing. And that's what Huffman lets us do. Now, the basis behind Huffman is that we go ahead and we grab a file. This is sort of what you guys are going to be doing. And in this file, we have characters ended by an EOF. We're going to talk about this sort of throughout the hours. But EOF basically is a character that represents an end of file. All right? Now, we wanted to go ahead and map the length of a word with, the frequency of a particular character with its representation, right? But before we do that, we actually have to count what the frequency of these characters are. So we go ahead and we do that, right? We find that these are the frequencies, right? Now comes the interesting part. Now, I'm not going to tell you how I did it, but I'm going to tell you why I did it. I went ahead and I built this tree. Now, this tree has at its leaves characters. So this leaf has a space. This leaf has a C. This leaf end of file. This leaf an A. This leaf a B. Right? Now, I went ahead and I put the most frequent things closer to the top. And I went ahead and put the least frequent things at the bottom. And the representation of any single one of like, for example, the representation of A is going to be 1, 1. And the representation of B is going to be 1, 1, 0. All right? So it sort of makes sense that I want the most frequent things at the top and the least frequent things at the bottom. Right? And we're going to use a tree to decide that for us and to help us do that. Now, something to note about this tree is, what do you guys think these numbers mean? What do those numbers mean? Yeah. Exactly. But what is this for? So the answer was correct, right? How often they appear in the text file. But why this for? What's this for mean? That's how often what appears in the text file? Exactly. All the ones under it, right? So it's going to be 2 plus 1 plus 1, right? So every single one of the nodes is sort of going to store the value or the number of frequencies of all the things under it, right? And so clearly we're going to have things that, like more common things, greater numbers at the top and smaller numbers at the bottom, right? This should look a little bit suspicious for you. We've seen things like this before. Now, this is generally what we want to do, right? We want to go ahead and we want to count the occurrences and place these characters into a priority queue. We're going to talk a little bit more about why that is. And then we're going to go ahead and create a Huffman tree. This algorithm we're going to touch upon in the next few slides. But once we do that, once we get this tree, with this tree, we can go ahead and create a map where space maps to 0, 0, 0, 0. A maps to 1, 1, right? And so on and so forth, right? Using this tree, right? Any questions about how we can convert a tree? We haven't talked about how to get this tree, right? We're going to work on that in a little bit. But just assume that we can create this tree, and it's the best tree ever. And then we go ahead and we can do this. Now, with this in mind, we can then go ahead and convert a file to binary using this exact sort of mapping, right? So here, for example, we grabbed A, and this 10 was B, and this C was sort of this. How did that go? A, and then B, and then space, and so on and so forth. All right? This is generally what the program does. Any questions about the general program? We're going to look at the algorithm right now. But it kind of makes sense, right? We're grabbing this. We're finding what the optimal way to represent these characters is. And then we're using that to write to disk, right? To create a new file with less sort of memory storage. Now, the way we build a tree is super, super interesting. Now, I mentioned a priority queue. Why do you guys think we want a priority queue? How could a priority queue help us? Chris touched upon this a little bit during last lecture. Now, when we looked at the tree itself, right? What is something we noticed about the numbers? They have the, sorry about that?
Like
Exactly. For each node, there's the value of the frequency. And how was this structured? Was this randomly structured, or was there a structure to it?
The highest frequency is at the top.
The highest frequencies are at the top, and the lowest frequencies are at the bottom, right? Now, let's say that I'm building this tree, and as I'm building the tree, I'm adding things to the top, right? So basically everything, I'm just sort of pushing down and adding nodes to the top. Do I want to start with the more frequent things or the less frequent things? With the more frequent things. No, we want to start with the less frequent. Why less frequent?
Because you're putting it on the top.
Exactly, we're putting it on top. We're not building at the bottom, we're putting on top, right? And so if we look at here, we go ahead and we put in a priority queue. We put all of our characters in a priority queue. And so things with the highest frequency are going to have the lowest priority. And the things with the lowest frequency are going to have the highest priority. Because we're going to be building this tree from the up down. We're going to be seeing this. So right now, what we do is we're going to grab the first two, right? So in this case, C and EOF. And we're going to create a simple tree with that. That tree is going to look like this. It's going to have 1, 1 as its 2 leaves, and then a 2. We're going to push this 2 and queue it back into this priority queue, right? Now we're going to grab the next 2 top things, right? Which are going to be these 2. What's going to happen now? Yeah. We make it exactly. We make a node for the top with these 2 as its children, right? Awesome. That's what happens. And we put it back into the priority queue, right? What's the next step? What's the next step? Someone else. What happens now? What were we doing previously? We were grabbing the 2 highest priority things. What are the 2 highest priority things right now? And this is the current state.
B and the A.
It's going to be exactly these 2 sort of nodes, right? So we go ahead, we grab them, and we make, what do we do out of them? We make 6, exactly, awesome. So we have 6. Now we have a priority queue of this. What do we grab now? What do we grab? Exactly, the 2 of them, 4 and 6. That's the only 2 things in our priority queue. We go ahead and we create another tree with both of these as the 2 nodes. And now we only have 1 thing in the priority queue. And so we're done. This looks awfully familiar. What is this? This is the tree we actually just had, right? We found a way to construct this tree where the lowest sort of frequency things are at the bottom of the tree. Why? Because we joined them initially and we built things on top of that, right? And we pushed them down the tree, and things with the highest priority we put at the top of the tree. Isn't that pretty cool? Any questions about this? This is kind of important.
So in the event with B and A
Uh-huh.
the same frequency,
Uh-huh.
what does it matter whether or not it's left?
It doesn't matter. So the question was whether, sort of in this case, right, when we get the B and an A, it doesn't matter which one goes to left or right or how that works. It doesn't really matter. You just grab the 2 lowest priority things. It's actually kind of cool. This is actually sort of proved to be optimal. And there are many different sort of proof systems as to why that is the case. But if you're interested, I definitely recommend you go and look at it because it's kind of awesome. But this is actually an optimal way of doing this, right? Yeah, question. Are we using linked lists? Not necessarily, right? Because for a linked list, it's a linear list of things, right? This is actually a tree, right? That's why it's called the Huffman tree. Because you have every node has 2 children, right? And so we're building this sort of tree, right? Now these sort of are pointers, right? So a tree, right, has a value associated to it and 2 pointers, right? So that's sort of what's going on here. All right, good question. Any other thoughts about this? All right, awesome. We can keep going. Now, when we go ahead and we have this tree, now we want to actually encode it, right? And so we arbitrarily say left is going to be 0 and right is going to be 1, right? It actually doesn't matter which way you choose, but we're just going to say 0 is left and 1 is right. And so now, given the position of items on this tree, we can go ahead and we can tell you what the binary encodings are of the things in it. So for example, here, space is going to be 0, 0. B is going to be 1, 0, right? What is end of file going to be? 0, 1, 1, right? Because we go here left and then right twice, right? So once we have this tree constructed, finding out what for a character its encoding is in this new language that we created, right, is. Any questions about this? All right. Now, from that tree, we go ahead and we create these encodings, right? So that tree sort of had this stuff, right? So now the text AB, AB, CAB is actually encoded in this manner, right? Using these encodings, right, from that optimal tree. And so now, when you put that all together, I'm going to go ahead and sort of, this is our final sort of file, what it looks like, right? Under the hood, this is actually what it is. So before, we had A with a byte, B with a byte. How many bytes did all of this take? So firstly, how many characters are in this string? In this string? 9, right? 9 plus 1 and a file, 10. Right? So there's 10 characters. Each character, given that in regular text file is going to be in ASCII, is going to have a byte each. So we're going to actually have 10 bytes. Now we went ahead and we Huffman encoded, and we actually brought it down to 22 bytes, which is 22 bits, sorry, which is about 3 bytes. The same information is now represented in the third amount of space. That's pretty cool. That's pretty awesome. Now, when we're decompressing, the same thing happens, but backwards. How do you guys think? If I give you this tree, what's going to happen? It's right up here, right? We go ahead and we read each bit one at a time. And we start going down the tree. For example, here with 1, we go 1, 0, 0, oh, B, right? And then the next one is going to be 1, 1, 1, A, and so on and so forth. And that's going to be our output, right? This is going to be BAC, ACA. That's what this is. Now, I have a question for you. Don't you need delimiters between characters? That sounds crazy. Like, how do you know when a character ends and the other one begins? How do we know that? Why don't we need something like a, I don't know, like something in between characters to let us know when the end of a character was and the beginning of another one is? Why? Oh, because it finds an answer, right? These are called prefix tree. And the reason is because any single sequence any subsequence before that doesn't exist in as an encoding. For example, here, 0, 1, 0. 0, 1 doesn't exist as an encoding. If it did, you wouldn't know whether to continue on to C or to whatever 0, 1 was. But in this case, once you reach the end of a tree, that encoding already exists, right? Like that's the end, right? And so we don't need delimiters, right? Once you get to the leaf, that's what that character is, and you keep going. Right? Any questions about that? This can be a little bit tricky. Yeah?
So it's not necessary to store a map of the shorter values to the characters because you have this tree.
Nice. So the question was, do we need to store a map of the shorter values with this text file, right? That's a great question. Now, ASCII is a universal language. So you can give a text file to your computer, and the computer will be like, oh, this is ASCII, I can just read it as regular text file. Now, when you give the computer this, and you tell it, read it for me, or you tell it, decompress it for me, they have no idea what that language is. You need to give them the language, like what all these bits are for that particular sort of string, right? And we'll talk about that in a little bit. Now, there's a cost to that, right? Because if you're including a map in a text file, there's some space involved in that. And so maybe when you're go ahead and compressing something like BAC, ACA, you're not really getting anything. However, if you're going ahead and doing the compendium of all New York Times articles of all history, then storing a little map at the end with the language that you're sort of dealing with, very, very much cost effective. All right? We're going to touch on this in a little bit. That's a good point. Oh, here we go. How do we know what the map for decompressing is? Actually, now is the point. We include the map in the file itself, right? So we have a map where we have the actual number for the character itself and what it points to, right? So 32 is going to be something in ASCII, and it's actually going to point to what the new number is, right?
That's actually the frequency, I believe.
It's the no, I think it's the number itself. Is it not? All right. It may be the frequency. Maybe you're right.
I thought all we were doing is exporting the frequency map.
Yes. Okay, then sorry about that. It's actually the frequency map. We're exporting the frequency map. All right? Because from the frequency map, you can always deterministically compute what that tree looks like. Does that make sense? So, how do we go ahead and we include a map in a file? What does that mean? I'll give you a quick hint. You can easily read and write like maps with the less than less than or greater than operators. All right. The spec sheet goes on a little bit about this. But a couple of functions that can be really useful, almost instrumental, are the read bit and the write bit functions. And so in read bit, you actually read a single 1 or 0 from a I-bit stream. So I-bit stream is, you know how sometimes we have sort of input streams that we read text from and we loop through text. Now we're actually looping through bits themselves. We want to look at the file in a bit format. And so sometimes we can read a bit with a 1 or a 0. We can also go ahead and write a bit with an O-bit stream, which writes 1 bit at a time. The int bit has to be a 0 or 1, otherwise it doesn't know what to write. And they're both members from the, they also contain members from the I/O stream, like open, read, write, fail, close. So it's very similar to when you're looping through a file, character by character, or line by line. The same thing applies here, but bit by bit. Any questions about that? All right, cool. Now we're going to actually look at the implementation of this and what we go ahead and ask of you. We provide you with something called the Huffman node, right? And the Huffman node includes these 4 main elements to it. One is the character, which is the character being represented by the node. This is something important. We're going to be representing characters with integers, all right? And so the reason for this is because we go ahead and we have these 2 different characters that are outside the range of what a character can hold. But basically, for this entire assignment, consider and represent characters as integers. All right, we go ahead and we express and we're very sort of clear about this in the handout. But if you see yourself writing the word char space, take a step back and think about what you're doing. All right, that's sort of my advice. Now we will go ahead and we have a count, which is sort of the number of occurrences of that character. So when we're looking at that tree, it's that number that was on the tree, right? And then we obviously have a 0 or a 1, which is going to be our left or right, right? Now, the character field we declare as int, but just think of it as a character, right? So basically it has an A or a B or a Z or a parentheses or what have you. It's going to represent one of 3 things. One is an actual character value, so one of these things. It can also represent the pseudo end of file. We define it in bitstream.h, but it basically every file that we give you, every file that you read is going to have this pseudo end of file. And the reason is because when you're reading a file, you want to know exactly when you've reached the end. All right. Once you start coding this up, you will see the magical properties of the pseudo end of file. We also have a quick thing called not a car in bitstream.h in Stanford Library, which means that sometimes these texts can be corrupted or they can have sort of weird bits. And so when you're reading, it might return not a car for a particular text. So if you're reading something in Hungarian, there may be characters in Hungarian that aren't represented by the traditional 255 sort of bit ASCII table. And so you have to go ahead and Stanford Library will return not a car. And so not a car, just treat it as if it were a regular character, right? Yeah, Chris.
You can also use not a car when you're determining the character for the nodes that don't have characters associated.
Yeah, so you can also use not a car for things that aren't characters, right? As Chris pointed out, which is basically nodes that don't have characters in them, just not a car.
Like the ones that are the nodes.
Yeah, like the nodes that are central nodes that have children. Those don't have a character associated, so you can just have not a car for them. Right? Good point, Chris. Now, We're going to go over sort of all the different functions that you're going to be writing. All of these pretty much follow identically what we've been talking about, for the last 30 minutes. And it's sort of that entire process, we go ahead and we decompose it down for you in these sort of little chunks that you then combine together. All right, so we try to make it bite-sized for you. So the first thing you're going to do is actually build a frequency table. So we go ahead and we give you an input, and you have to count and return a mapping from each character, which remember, we're presenting as an integer, not as a character, to the number of times that that character appears in the file. Right, so we're going to actually be returning a map of every character to its count. All right? Any questions about that function? I think generally makes sense, right? Now, build encoding tree. All right, it's a little bit trickier, right? So build encoding tree will actually accept a frequency table and will create a Huffman encoding tree based on those frequencies. It'll return a pointer to the node of that tree. So basically, as we saw earlier, that tree that we built with the priority queue, that's going to be within build encoding tree, because that's where sort of the heart of the algorithm will be. Then we're going to be going and building the encoding map. So giving this encoding tree, I want to return a map. I want to know what the language is, and that language is going to be the specific character pointing to what its new value is in binary, right? And so it goes ahead and accepts a pointer to that root of that Huffman tree and uses it to create and return a Huffman encoding map based on that structure. We saw how that generally worked earlier today. For example, if character A has the binary value 1, 0, the map should store key value pairs as A, 10, B, 11. All right? Any questions about that? All right. We also want you to go ahead and encode data. So basically, we will give you an input file, and we want you to read one character at a time from that input file, and use the encoding map, which was provided to you, but which you created, right? To encode each character to binary, right? So given an input, you go ahead and you use the sort of what's given to you to write the binary bits to the output stream, right? We went over a little bit what are the functions that are useful to writing to an obit stream, right? Obit stream is going to be write bit, sorry, and for the ibit stream is going to be read bit, right? So the same way that encode data goes ahead and reads and encodes into the output, here we're going to be doing the opposite. We're actually reading bits from the input file one bit at a time, and recursively walking through the specified decoding tree to write the original uncompressed contents of that file to the given output stream. So basically, we're grabbing this input stream of bits, we're doing some magic to it, and then we're going to be returning the, like in the output, we're going to be printing out the actual sort of string in, I guess, in English, right, or in ASCII, right? Does that make sense? It can be a little bit confusing, right? Now, once we have all of this, we can put all of that together. And so you're going to write a function, method, compress, sorry. And compress is the overall compression function. We give you a file, and you take this as parameters, and you want to write to the obit stream that is the output. You should read the input file one character at a time, build an encoding of its contents, and write a compressed version of that input file, including a header. That header was that map that we talked about earlier, right? You can just go ahead and put that map at the beginning, and then you can also read that from the beginning, so that you know what language you're using, what language you built for your Huffman tree, to that specified output file. All right. You should definitely build this. Not just that. You definitely will build this on top of the other encoding functions, and call them as needed. Right. We went ahead and we made those separate functions for you just to make it easier for you to approach this problem. But definitely, use those when you're building compress, right? That's the whole point. Any questions about compress? Yeah.
So for decode, we read one bit at a time, and from there we get a character. But we have our Huffman encoding map is from character to like bits.
So you say in decode, we have, because decode is used for decompress.
Yeah, yeah, we're going from bits to characters, but
Yes.
the map we make is from characters to bits. So how would be like?
The map, so that exact map, you can just use regular ASCII to it. Does that make sense? So you're actually, you're not, like, so let me see if I understand your question correctly. Maybe I'm misunderstanding you. But you say that we have a map, so we're compressing things, and how do we put this map at the end? Or like, what is the question?
Like, would we need a second map that like stores the like our new bits, and like given a sequence of bits, we like go into a character?
Do we need a, why would we want this map, this new map?
Because we're reading bits from the file,
Mm-hmm.
from like the output file that we're going to decompress.
Mm-hmm.
And wouldn't we need like some way of saying like, oh, here's a map where
I think we're traversing the tree and we're reading the bits to get the character.
Oh,
As
okay.
opposed- Is that right?
Yeah, that's correct.
okay.
Yeah, that's sort of what, with one map, you can go ahead and do everything for you, right? And that map, just use regular ASCII to it, right? There's some tricks that you could do to like make that map represented in like less bits, I guess, but you don't need to worry about that, right? So that map comes in like when you're compressing things down, right? You're going ahead and we're grabbing this map and we're putting it in ASCII, and then we're putting the rest of our compressed file at the end. And later on, when we're reading, we're actually grabbing the map as ASCII and then using that to sort of, I guess, put everything back into ASCII. All right?
But when you're reading the file,
Yeah.
you know where the map ends and the encoding starts.
So the question is whether, like, how do you know how the map ends and the question starts? The handout goes into specifics into that. I sort of did my best right now to not go into like the very nitty-gritty implementation details, just so that it's easier for us. But the handout sort of specifies exactly how that would work. So the final sort of function that we need to write is going to be decompress, sorry, and this should do the opposite of our compress. We're actually reading bits from the given input file one at a time, including our header, which is going to be inside the start of the file. We can actually look at this at the end because we're sort of ahead on time. And then we're going to write the original context of that file to the file specified by that output parameter. So we're going to pass it in an O stream, and you're going to put things into ASCII, right? Using, once more, a lot of the same functions that you created earlier. All right? Any questions? We're going to look at this right now, actually. How do we go ahead and we do that header? That was a great question. But any questions before that? All right, awesome. We can go ahead and let's open up the CS106B. Any questions generally about Huffman encoding? I know this was a lot of information dump because there's a lot going on here. But this is sort of, it's important that you understand intuitively what's going on and what the reason is behind all the decisions made and what the algorithm is, just so that when you sit down and start coding it, it's going to be much easier for you. So if we look at encoding the header, here we go. So we're writing the encodings into the compressed file, right? When we open it later, the first several bytes will store an encoding information. And those are going to be immediately followed by the compressed binary bits that we compressed earlier. When we could come up with, yeah. Interesting. Chris, do you know how that works? How you know when the end of a header, like when you're reading in, how the end of a header oh, I think that the way to do that, oh, yeah, I think I know. So the way to do that is that you can go ahead and when you're printing out a map, you use the less than operator, right?
Oh, right. And then you do the same thing.
Yeah. You use the same thing to create a map, right? So what you can do is you can grab this, you can create a new map, and from this input stream, you sort of do greater than to that map, and you're actually going to be building that map I believe that is the way to do that. Does that sort of make sense?
But that stream includes the map as well as the encoded data. Doesn't it?
That, yes, but it's only going to grab the initial, the same way that when you're writing to let's say you're writing to the console, there's things that are already included that are like words in the console, but when you're putting things in it, you're adding things to the end. In this case, when you're doing that greater than sort of operator, it knows when to end, like when the end of what defined the map is. So like,
Brace or whatever.
it has what?
I think that the curly brace.
Yeah, it has like
It
a,
does the map, it does the curly brace on both sides.
exactly, it has like a, so here we look at what the map is represented as. It has sort of a curly brace at the end. So it can just like, it has its own like end of file. Does that sort of make sense? So it knows when to stop reading the map itself.
Okay, so the first read from the stream into a map object automatically grabs.
Exactly. So yeah, yeah. So the first read, just to repeat that for the camera, the first read is going to grab everything from what the map portion is, which it knows from the front of the input stream to a map, and then you can use the map to start decoding the remaining portion, right? Which is that compressed portion, right? Great question. Any other questions about Huffman encoding? How do you guys feel about this? So thumbs up if you feel great, ready. I could code this right now and go to bed, before midnight. Sort of this way if you're like, all right, and thumbs down if you're completely confused. All right, I see roughly up and middle. All right, awesome. Sort of, yeah. Do you guys have any questions? We can also talk about this sort of after hours, but thank you guys for coming. I hope this was useful for you guys. We're going to be putting up these slides on the website, but I recommend you guys take a look at Huffman encoding during the break if you want to. You don't have to, right? But it's definitely not an assignment that you can sort of complete in one sitting, just because there's a lot going on, a lot of moving parts, and a lot of points where your code could go wrong and you can have lots of bugs. And so definitely it's something where you work iteratively, and the handout itself specifies what is the most optimal way, or like, what is the recommended way at least, of approaching sort of Huffman encoding itself. All right, awesome. Well, thank you guys for coming. Have a great Thanksgiving.